Greetings, this is Mr. Kingsbury, and today we're going to talk about something called absolute value functions. So as with every family of functions, we're going to start by looking at the parental function, or the parent function. That would be this guy right here. So our absolute value, when you graph it, is going to look just like a V. Now the equation looks like this. You may notice there are a couple of interesting looking bars right there. Those are the absolute value bars. And what absolute value does essentially is it measures the distance something is from zero. We're going to come back to that idea in just a second. To represent that that's what we're doing, we put these little bars there. And I will say that distance is always positive. There is no such thing as a negative distance. So whatever goes into these bars comes out positive. Certainly if it's positive, it will come out positive. But if it is negative, it also comes out positive. Our transformation equation is going to look like this. Please note, we're not using function notation anymore. We actually have absolute value bars in here. So from here on out, all of the function families we see will make our function equations a bit more specific, which is kind of nice. All right, so what characteristics do we have here that are important? Obviously, the x-intercept, which is 0, 0. The y-intercept is also 0, 0. Guess what else? The vertex is 0, 0. And there's an axis of symmetry that goes right through it. That would be x equals 0, although that is outlined right in here. I do want to point out this very important thing. In the transformation equation, the points C and D make the vertex. And that's going to be super important when we talk about this next piece. So you're going to want to be able to read this transformation equation and get the C and the D value out so that we can write these things kind of differently, actually. So you're going to see us write the equations like this, but then also we're going to talk about how they can be written piecewise. When we do that, we use the vertex point. Specifically, we use the x value of the vertex point to restrict the domain. But we'll get to that in a second. Speaking of which, the domain for this is always all real numbers. And the range will either be y is greater than or equal to the y value of the vertex, which is d, or y is less than or equal to d, depending on whether it opens up or it opens down. So let's talk about a piecewise function. I'm not sure if you've heard that phrase before, but piecewise means made up of several different pieces. So we can look at absolute value as not just one whole graph, but rather two different graphs that are connected and that have their domain restricted, and that's why we're only seeing part of it. See, this is a line, and this is a line. So we can look at our absolute value graphs here, or absolute value functions, as two lines that have a restricted domain. Now, how do we do that? You're going to need to know, because this is part of what's on your test. So to do that, we're going to do a couple things. First of all, we need to identify the vertex. And here on number 1, it says identify the vertex as h, k. That is actually a reference to a form of the equation called the vertex form. It looks identical to our transformation notation. So we're going to use C and D instead because that's what we've been using for transformations. So let's change this from h, k to C, D. It amounts to the same thing. And we will use the x value or the C value to restrict the domain. What we will do is we will use either x is greater than or equal to that x value, or x is less than that x value. And that's just the restriction part. How do we come up with the equations? Well, first, we drop the the absolute value bars. And then what we'll do is set up two possibilities. See, I mentioned before that absolute value measures the distance something is from 0. There are always two things that are the same distance from 0. For example, if I asked you what number was 3 units from 0, you would probably tell me positive 3, because that is absolutely 3 units. 100% true, but you know what? Negative 3 is also 3 units away. So both of these numbers are 3 units away, which means both of these numbers have an absolute value of 3. So when we're looking at absolute value equations, we have to consider all possibilities. And it turns out that one of those gives us one side of the graph and one gives the other. So what you're going to see me do is we'll take the equation, I will drop the absolute value bars, and I will replace them with parentheses, because these are still a type of grouping bars, and I still need to group these things. So I'll replace them with parentheses, and one of them I will simply just rewrite what's here. The other one I will put a negative outside the parentheses. That gives me the positive and the negative values that have the same absolute value. So I do one positive, I do one negative, and then I will simplify a little bit, and I'll have my 2 equations. And then I need to make sure that I use the domain restrictions. So let's do a few of these, just so you can get a feel. Let's start by coming up with the equations. We have f of x equals the absolute value of x plus 4 minus 2. So to come up with the 2 equations, I'm going to drop the absolute value, and I'm going to put parentheses there instead. And don't forget that it still equals f of x. And then I'm going to rewrite this, and it will look almost identical, except for one thing. I'm going to put a minus right there. So I rewrote this with parentheses instead of bars. I just put a negative outside of one. The other one stays absolutely the same. Then from here, I'm going to simplify some things a little bit. I don't actually have anything outside these parentheses, so I can drop them. And then once I do, I can combine positive 4 and negative 2. So I get x plus 2, because 4 minus 2 is 2. So this is f of x equals x plus 2. That's one of my lines. The other one, let's find over here. Now notice I have a negative out here. I'm actually going to put a 1 in there, and I'm going to distribute the negative 1. So I get f of x equals negative 1x minus 4, and then don't forget the minus 2. And then lastly, I will combine my like terms. So I get f of x equals negative 1x minus 6. So now I have the 2 lines. But if I were to look at a graph of these, I would actually see an x, because the lines go on forever in 2 directions. That's what they do. So I need to limit them. And an easy way to do that is to look at the slope, right? So this is technically a positive 1. This is a negative 1. So this slope is going this way. This slope is going this way. So you want to pay close attention to that. That is helpful. Also, we need to know, how are we dividing these guys up? How do we make sure to put the right limits in the right places? So that's where the vertex comes from. So I'm going to look here, and remember that our equation is f of x equals a times the absolute value of b times x minus c plus d. Doesn't look like we have an A or a B, but it looks like we have a C and a D. That tells me my vertex is, this would be negative 4, right? We change the value, the sign of the C value, and then D stays the same. That would be negative 2. We don't change anything there. So that's my vertex, is negative 4 and negative 2. Now of that, I don't really care about this. I care about this. One of these lines will be looked at from everything greater than negative 4, and the other one will be looked at from everything less than negative 4. And the question is, how do I know which one goes where? And again, it has to do with the slope. It also depends if it's open up or open down. And I'm trying to think if there's a quick way to show you how to do this. What I know is out here, to begin with, it was positive. Right? So it was positive here, which means this side with the positive slope is going this way, and this side with the negative slope is going this way. So I will write my domain restrictions. I couldn't think of the word, sorry. So over here, we will go, it will be -4, and this will be x is greater than or equal to -4. And what I want you to do is just always use greater than or equal to. And then over here, we will do x is less than -4. And what that does is it makes us only look at the piece of this line that exists for all x's that are less than -4. And we'll only look at this line for all of the x's that are -4 or bigger. That's how you do that. I am trying to think if there's a better way than the slope. Certainly you can match it up. What I'm thinking is when the slope is negative to begin with, that means then that the negative is going to get the greater and the positive is going to get the less than. And that's kind of confusing. So, yeah, trying to think if maybe there's a better way to do this. But let's look at another one and walk through it. So we got g of x equals -2 times the absolute value of x plus 11. Let's break this into our two pieces. So we will have g of x equals -2 times x plus 11, and g of x equals +2 times x plus 11. And I will simplify this. It really doesn't simplify a whole lot. I mean, you can quote unquote, I'm making air quotes, there's my air quotes, distribute this, but there's really nothing to distribute over per se because there's nothing being added or subtracted in here. This is just really g of x equals -2x plus 11. And the same thing's going on over here. It's just g of x equals 2x plus 11. And I figured out what we're going to do. So the one that you didn't have to change is always going to get the x is greater than or equal to. And the one that you did change will get the x is less than. And then we just need to figure out what our c value is. And our vertex, I guess. Please note, there's no c value in here, right? If I write this, write the equation, I got g of x equals a times the absolute value of b times x minus c plus d. I certainly have a d value here. And my a value would be -2. I'm not really concerned about that because I need c and d for my vertex. There's nothing in here. What number means nothing? That would be 0. So my vertex would equal 0, 11. C value is 0, D value is 11. And again, I want to focus on this. So I'll put that here and here. All right. I'm trying to make this as much a process as I can because I want you to be able to do these without having to think a whole lot. Let's try another one and see how we do on this one. So we've got h of x equals 2/3 times the absolute value of x minus 5 plus 6. It just occurred to me, it might be easier if we do, we identify A, B, C, and D first. Looks like my A is 2/3. My B is non-existent. My C would be +5, and my D would be 6. That means the vertex is 5, 6. Probably easier if we do that first. Now let's split it up into our two equations. So we've got h of x equals 2/3 times, and instead of absolute value, we do parentheses, right? X minus 5 plus 6, and then the other one would be h of x equals 2/3, -2/3, I'm sorry, times x minus 5 plus 6. Cool. And then we follow PEMDAS. So I will distribute 2/3. That gives me 2/3 x minus 10/3 plus 6. And I'm actually going to make this 6/1 and multiply by 3/3. Why would you do that, Mr. Kingsbury? I'm glad that you asked, because I'm going to need to add these two things together, right? I'm going to need to add -10/3 and +18/3. So I thought I would adjust the 6 so that I had common type denominators there. So we get h of x equals 2/3 x, and when we put these two together, -10/3 and +18/3 gives me 8/3 like that. Then we'll go over here. We'll do something similar. I will distribute the negative 2/3 x. So negative 2/3 times x is negative 2/3 x. Negative 2/3 times negative 5 would be positive 10/3. Plus, I'm going to do the same thing with this 6. I'm going to multiply it by 3 over 3. So I get 18/3. I have now adjusted it, and I can now put these together. So I get h of x equals negative 2/3 x plus 28 over 3. And now the only question is, how do I restrict the domain? No big deal. This is the one that we didn't have to change. This is the one that looks just like what we started with. We didn't have to make it negative, so this will get the x's greater than or equal to. This is the one that we did have to change, so this will get the x's less than. And then remember, we just used the c value, so we put 5 and 5. Hey, that worked pretty good. Let's try one more. And then I can just show you how to solve these things. And I apologize that the video is taking a long time, but I'll try and be faster. Last one here, and this has got almost everything. We've got k of x equals negative 4 times the absolute value of x plus 8 minus 5. Let's find out what our a, our b, our c, and our d are. So let's see, we would have a times the absolute value of b times x minus c plus d. There's my d. There's my c. This is an a. Doesn't look like I have a b. So a is negative 4. B we're not going to worry about. C is, it looks like it's negative 8, but remember we changed the sign. So I'm sorry, it looks like it's positive 8. So we changed the sign and it's negative 8. And then right here we got d is negative 5. Then we split up our equation into two pieces. So we've got k of x equals negative 4 times x plus 8, in parentheses now, right, minus 5. And then we'll do k of x equals positive 4. So we'll change the sign to positive 4 times x plus 8 minus 5. I don't know if you've caught on to this, but the other times that we've done this, we changed the positive to a negative, and now we're changing the negative to a positive. Well, I guess on number 2, we also changed, we changed a negative to a positive instead. I'm just bringing it up because I don't want you to think we're always making it negative. We're not. We're doing one exactly the same way that it is, and one we're going to change the sign in front. So if it starts negative, we make it positive. If it starts positive, we make it negative. All right, just FYI. Store that away. Put that in your hat, whatever. Oh, I forgot to mention the, well, never mind. So let's follow a little PEMDAS here. We're going to distribute the negative 4. So k of x equals negative 4x minus 32 minus 5. And then I'll put my like terms together. So k of x will equal negative 4x minus 37. And since this is the one I didn't change, I will put the x's, should be greater than or equal to the c value of negative 8. Over here we'll do a similar thing. We'll distribute the 4. So we get k of x equals 4x plus 32 minus 5. Then we'll put the like terms together. So k of x equals 4x plus 27. And this is the one we did have to change. So we will give it the x is less than, and then we do the c value of negative 8. And there you go. That's how you write it piecewise. Next up, we're going to talk about solving these things. And we're actually going to spend an extra day on this, but we need to talk about it now and get started on it now. So the first question I have is, what is the order of operations, and how does it help us solve? And the short answer is that the order of operation is PEMDAS, which is parentheses, exponents, multiplication, division, addition, subtraction. You all should all know that. How does it help us solve for unknown variables? Well, actually, let me finish defining it first, because then I can use that to answer this other piece. PEMDAS is the order of operations, and it tells us the order that we simplify expressions in. So how does it help us solve for unknown variables? By working it backwards. We can solve an equation. So that's how it helps us. Just good to be reminded about that. So how do we solve absolute value equations? Much like when we were writing the piecewise functions, we're going to split it into two possible situations. Because, again, there are two values that give you the same absolute value. So we have to check both of them. And what we'll do is, just like with the piecewise function exercise, we will split the equation into two separate equations. And we will make one positive and one negative. We will solve both. And then you have to check your answers, unfortunately. There is this situation that pops up with absolute values where, because we're only looking at parts of those two graphs, when we remove the absolute value bars, the pieces we weren't looking at come back into play, and we could, without realizing it, find a solution that's on that part of the line, which is not part of our graph. So we have something called extraneous solutions. Extraneous solutions is a solution found by solving, like you would normally, but it doesn't work when you put it into the original equation. And again, the reason for that is the equation we will solve will not have an absolute value sign in it, or absolute value bars, but the equation we plug it into will. Now, I have a bunch of these here, and I don't know that I have time to solve them all, but let's pick a few. Certainly we can start with number 5. That's a very simple one to solve. So we've got the absolute value of b equals 5. Oh, I should mention, because I didn't mention it, the steps are this. First, you've got to get the absolute value piece by itself. So you use PEMDAS in reverse, like you would to solve normally, to get the absolute value part by itself. Then you drop the bars, and you make your two equations, and then you continue solving like you would both of those two equations. And I'm going to demonstrate that for you right here. I thought I would mention it, though, because there's actually nothing outside these bars to drop. So the first thing I can do is set up that either beta equals 5 or beta equals negative 5. So that's all well and good. And actually, there's nothing to solve here. That's one of the reasons I picked this, is it's very simple. So I basically have my answers. I just need to check them. So I'm going to plug these back into the original equation. What is the absolute value of 5? Well, that would be 5. Did I get a true statement? That's what we're looking for. When you plug in your answer and you work PEMDAS, do you get a true statement? This is true. And by the way, you're going to work both sides separately. This is not a great example for showing that. You will see other better ones here in just a minute. Let's try the other side. Is the absolute value of negative 5 equal to 5? Turns out it is. So both of those work. And that's how you solve one of these bad boys. Let's do one that's a little bit more intense, I guess. A little more involved. I'm going to do 6 and 7, I think. I'd like to do all of them, but I unfortunately don't have that kind of time because this video is getting long. So here's number 6. We've got 2 times the absolute value of, I'm going to just use x, minus 4 equals 8. Now you'll note that there is a 2 outside the absolute value bars. I need to get rid of that first. We have 2 options for canceling stuff. With addition and subtraction, we make a 0 pair by using the opposite signed number. With multiplication and division, we use the opposite operation and make a 1. Pardon me, I've had very little caffeine this morning. So there's that. In this case, and some people don't catch this, so I want to make sure I'm really explicit about it. This is 2 times the absolute value of x minus 4. That's multiplication. To undo multiplication, I use division, and I will divide by what I'm multiplying by. So I'll divide by 2. This gives me a 1, and 1 times the absolute value of x minus 4 is the absolute value of x minus 4. On the right side, 8 divided by 2 is 4. Now that I have the absolute value part by itself, I can write my 2 possible situations. One of them would simply be x minus 4 equals 4. On the other one, I will write this, but I'm going to change the signs on the left. So instead of x minus 4, I'm going to do negative x plus 4 equals 4. And what's really interesting about absolute value equations when you're solving them is a lot of times you will use the same steps, but because I'm so sorry, I did that wrong. I should have wrote x minus 4 equals negative 4. You change this. That's my bad. I'm very sorry about that. At any rate, let's finish this. And let me finish my statement. So the interesting thing about solving absolute value equations is a lot of times you will use the same steps to solve, but because the number on the right side here is different, one is positive, one is negative, you'll get very different results. So right here I got x minus 4 equals 4. To undo a negative 4, I use a positive 4. So I add 4 to both sides. I get a 0 there, and x minus 0 is x. 4 plus 4 is 8. So one possible answer is 8. I'll do the same thing over here. I got x minus 4 equals negative 4. I'm also going to add 4. And once again, on the left, these make a 0 pair, and x minus 0 is x. On the right, though, I now have negative 4 plus 4 instead of positive 4 plus 4. Negative 4 plus 4 is 0. So my other possible solution is x equals 0. Now I need to check and make sure that these are correct. This is checking your work. We could have extraneous solutions. So I'm going to go back to the original equation and plug in there. So for this one, I will 2 times the absolute value of, instead of x, I will use 8. Absolute value of 8 minus 4 equals 8. Now you do the two sides separately. You will, when you're checking your work, you never add something to both sides or subtract something from both sides or divide both sides by something or multiply both sides by something. Never. You look at the sides as separate, you work them separately, and then you see if you get that true statement at the end. So I'm going to follow PEMDAS on the left here. We go inside the absolute value. What is 8 minus 4? That would be 4. I still have 2 times the absolute value of 4. There's nothing else going on inside those bars, so I'm going to go ahead and take the absolute value of 4, which is 4. So this just went from 2 times the absolute value of 4 to simply 2 times 4, which is 8. And then I bring down, I'll work the right side. There's really just a number, so I'm going to bring it down. Is 8 equal to 8? Is that a true statement? It is. That means our answer is correct. Let's try the other one. So we got 0 here. Let's plug that in. So we'll do 2 times the absolute value of 0 minus 4 equals 8. Once again, we do each side separately. Start with the left. 0 minus 4 is negative 4. So I have 2 times the absolute value of negative 4. The absolute value of negative 4 is positive 4. So this becomes 2 times 4, which is 8. On the right side, I just have the number 8. So I'm just going to copy 8 all the way down. Boom! Is 8 equal to 8? It is true statement. Both of these are solutions, which is awesome. I know I said I was going to do 7, but I actually think that I want to do number 9 for you because there's a variable over here, and I'm afraid you guys are not going to like that very much. You're going to say, how do I deal with that? And actually, we do it just like we did with the other two. We change the signs. Or at least when we split it apart, we'll change the signs. I'm getting ahead of myself. Let's start with number 9. We got 5 times the absolute value of p plus 10 equals 5p. And remember what I said. The first thing you have to do is get that absolute value piece by itself. So to do that, first I'm going to cancel this plus 10 by making a 0 pair by subtracting 10. And I know what you're saying. Kingsbury, you can't subtract 10 from 5p. You're right. I can't. What I'm going to do then is write what I would do if I could. I would do 5p minus 10. Over here, 10 minus 10 is 0, and 5 times the absolute value of p plus 0 is just 5 times the absolute value of p. See, so are the absolute values by themselves? Not yet. I'm still multiplying by 5. The opposite of multiplication is division. So I will divide this by 5, and I need to divide the other side by 5. And you can do this one of two ways. A lot of people like to put just one divide and go into the whole thing and put your number underneath it. I like to do them separately. You will see why in a moment. So on the left, 5 divided by 5 is 1. 1 times the absolute value of p is the absolute value of p. Then over here, we've got on the, was that the right? We've got 5 divided by 5 is 1. 1 times p is p. Negative 10 divided by 5 is negative 2. So now we have our equation, right? Now we've got it simplified a little bit. We've got the absolute value part by itself. Now we can do our two possibilities. So we'll go p equals p minus 2. The other possibility is that p equals negative p plus 2. Remember, you change the signs. And then we will solve this. Here I will solve by subtracting p from both sides. When I do, p minus p is 0. P minus p is also 0. 0 minus 2 is negative 2. Is 0 equal to negative 2? It's not. That is not a true statement. Whoops. Yeah, the p's got all canceled. So there's no solution there. We haven't even checked the work. There's no solution. That's crazy. Let's check the other side. So on this side, we will add p to both sides. I get 2p equals, this is 0, 0 plus 2 is 2. So now I have 2 times p equals 2. I undo division with, undo multiplication with division. This gives me a 1, and this gives me a 1. 1 times p is p, and then 2 divided by 2 is 1, so I write that there. So this is an interesting problem. I'm glad that I did it, because you can tell right off the bat here, one of our possible solutions didn't even manifest, because the p's all canceled. What's up? We do have this one, though, and we've got to check it. So let's plug that back into our equation here. So we're going to go 5, I meant to put an absolute value bar, 5 times the absolute value of 1 plus 10 equals 5 times 1. Again, we're going to do each side separately. I think I forgot a parenthesis right there. So we'll do 5 times 11, which is 55. And 55 plus 10 is 65. Then we will do the right side. 5 times 1 is 5. Is 65 equal to 5? And the answer is no. Which means p minus 1 is not an answer. Which means there is, since nothing works here, we didn't even get one out of there, no solution. I will make sure to post a completed version of the notes so that you can do the other 3 if you would like. Thanks for playing, and I apologize for the video going on so long. Bye.